Hey, welcome back to another digital replay. Today, we're working through the last little bit of momentum and energy, which is Unit 3, on pages 453 to 458 of your textbook, and this is energy conservation. Do you remember this? This is when we were talking about momentum. Here are two carts stuck together, and we're going to explode them apart. And what we found out was that the total momentum of the system before we exploded them apart was actually equal to the total momentum of the system after they have separated. So before the explosion, after explosion, the total momentum is the same. And in a collision, the same thing happens. Whatever the total momentum of the system is before the collision, that is the total momentum of the system after the collision. So once again, the momentum before and after a collision or an explosion is the same. We call this the conservation of momentum, and we call it a law of conservation of momentum. Well, it turns out that there is another law we need to focus on, and that law is the conservation of energy. And the law of the conservation of energy states that energy cannot be created or destroyed. Energy can be converted from one form to another in a closed system. The amount of energy at the beginning of the process is the same as the amount of energy at the end. Now I'm going to go through several examples of how this is true. So please stick with me, but know that what we're trying to prove here and what we're talking about here is that whatever the energy is at the beginning, that's what the energy is at the end. The energy, there cannot be new energy, and their energy cannot escape. It's only going to change forms. Now, we've mostly been talking about mechanical energy, and the total mechanical energy of a system is the kinetic and the potential energies added together. So whatever the total energy is before an event is the total of the kinetic and the potential energies, or the total sum of the kinetic and the potential energies. And whatever the total energy is after in a mechanical system is the sum of the kinetic and potential energies. And because of the conservation of energy, these two things are equal. They are the same. So let's take this little roller coaster guy. Now notice as this little roller coaster guy starts really high up here and comes down, we see these little sliders change here, kinetic energy and potential energy. If you remember, kinetic energy is dependent upon mass and velocity, and potential energy is dependent upon mass and height of the object. So you can see as the little roller coaster guy starts out really high, we have a high potential energy. As it gets lower to the ground, it has no potential energy. It gets high again, the potential energy goes up, it comes back down, the potential energy goes down. And as the little cart speeds up, we have more kinetic energy. And as it slows down, we have less kinetic energy. But the total stays the same. So if you were to add the kinetic and the potential energies through this whole roller coaster ride, the total energy would remain the same. All right, let's start with the example of Wile E. Coyote and the Roadrunner and a dropping object. And we're going to drop an anvil on Wile E. Coyote because that's pretty, non-violent and safe, right? Okay, let's get out our piece of paper, have a falling object here. Now at time 0, the object is hovering using some kind of cartoon forces in the air. And the total energy, recall, is the kinetic plus the potential energy. Kinetic energy is 1/2 mv squared. That's how we calculate it. What is its velocity right now? Well, its velocity is 0. So the kinetic energy of the object is going to be 0, or 0 joules. The potential energy is calculated using the mass and the height and the acceleration due to gravity. So it's at its maximum height now. And so we're going to call that height 100 meters. Okay? Just for easy calculations. Now our potential energy is going to be 98,000 joules. So what's our total energy going to be? The total energy is the kinetic plus the potential, or 98,000 joules. All right, cool. Let's let it fall a little bit. Keep that number for safekeeping. And let's let the object fall just a smidge. Okay, stop. And let's calculate the total energy now. Again, we'll use the kinetic energy is kinetic energy is 1/2 mv squared. It has a velocity now, so now it has a kinetic energy, 4,900 joules, let's say. And the potential energy, it's not as high anymore. It's not 100 meters. It's fallen a little bit. So the height has changed. It's gotten less. It's gotten closer to the ground. So our potential energy is less. But if you add them together, you still get 98,000 joules. Once again, this is the conservation of energy. It's going to be the same energy regardless. Okay, so at time 2, let's let it fall a little bit more. Same equations. Now we have a new kinetic energy. It's falling a little bit faster. Here's our kinetic energy. Here's our potential energy. It's not as high, so our potential energy keeps decreasing, but the total stays 98,000 joules. Let's let it fall a little bit more. It's falling a little faster now, so our kinetic energy is increasing. Our potential energy is decreasing, but the total stays the same. We're going to do this 2 more times. Fall a little bit more. Kinetic plus potential, 1/2 mv squared. Here comes our kinetic energy is hiking up there. We're at 78,000. Potential energy, we're getting closer to the ground, so our potential energy is going way down, but our total stays the same. Last one, boom, sorry Wile E. Coyote. Now our kinetic energy, 1/2 mv squared, we've reached as fast as this thing is going to go. And now our energy for the thing is 98,000 joules. Our kinetic energy for the thing is 98,000 joules. And our potential energy is 0 because we are at 0 height. Our total is still 98,000 joules. All right, let's look at the numbers here. So here's our table of numbers. Here's our table of values. Notice that the total energy throughout every single moment of that process stays the same, but the kinetic and the potential energy changes. Why is that? Because energy cannot be created or destroyed. It can only be transformed into another form. So in mechanical systems, we can transform potential energy into kinetic energy or kinetic energy into potential energy, just depending on how fast it's moving, how high it is, where it's going. These are the things we can do in mechanical systems. We cannot create or destroy energy, but we can change its form. Energy is conserved. Energy is conserved in a mechanical system, and energy can be converted from one form to another. That is, it can be transformed. Let's take the example of the bottle rocket, and the only part that I want you to focus on is the part when it leaves here. So when the bottle rocket is off of the launch pad, and we're going to call that height 0. Okay, so at height 0, the lowest height, the potential energy of this system is going to be 0. And the kinetic energy is going to be based upon how fast it's going, and let's just give it a value of 100 joules. Okay, so what's the total energy of this system? 100 joules. That's the total energy, the potential energy plus the kinetic. It's 100 joules. At the mid, so if you stepped all the way back and you could look at where that rocket was going, and you could see its highest point and its lowest point all in one frame, right in the middle, right in between the ground and the highest point that rocket would go, the potential energy and the kinetic energy would be equal, right at that middle spot, because it has to add to whatever it was down here when it was at the lowest spot. Down here, it was 100, so up here, the potential energy and the kinetic energy still have to add to 100. So each one, they would be equal, which would be 50 joules. Okay, so now let's go to the tippy top, the highest this rocket is going to go, the maximum height of the rocket. What will be the kinetic energy? Well, if you're watching the rocket, what do you notice? You see the rocket go pew, and it slows down, and stops just for the briefest fraction of a second before it starts plummeting back to Earth. And in that fraction of a second, its potential energy is going to be the highest, and its kinetic energy is going to be 0. But the total energy remains the same. The kinetic energy was converted to potential energy, but the total amount of energy stayed the same. Okay, so here we have quite possibly the most bizarre skate park ever. But in this we're going to look at pendulum motion. Okay, so what this skater is going to do is he's going to move back and forth across the screen in the same motion that a pendulum would make. Now I have him going in slow motion so we can actually watch his motion very closely. But what I want you to see is that the total amount of energy is staying the same. But look what's happening to the kinetic and the potential energy. As potential goes down, kinetic goes up, and as kinetic goes down, potential goes up. And notice where the highest potential energies are. Well, they're at the highest points on the skate park track, right? Or the highest swings of the pendulum. So as high as the pendulum gets, that's where the highest potential energy is. Look where they're equal. They're equal somewhere about here at the midpoint, right? And look where kinetic energy is highest. Well, it's highest where he's going the fastest, which is right there down at the bottom. And they're equal here, and then potential energy is the highest. So in a pendulum motion, you have the highest potential energies up at the highest points that the pendulum swings, the highest kinetic energy down here at the base, and then they're the same about right there. But the total amount of energy of this pendulum or of this skater in the weird skate park stays the same. To restate the conservation of mechanical energy, we say that the kinetic energy plus the potential energy at the beginning, so the total energy at the beginning, is equal to the kinetic energy plus the potential energy at the end, the total energy at the end. The total energy at the beginning is equal to the total energy at the end. That's the conservation of mechanical energy. So the total energy of a system is the kinetic plus the potential. The energy is conserved in mechanical systems. In a perfect mechanical system, energy is transformed kinetic to potential and potential to kinetic. That's been Digital Replay. Hope this helps. If you have questions, comment below, email me, or see me in class. We'll talk to you next time.